Good afternoon. Whoa. And welcome. My name's Will. I know you have a choice in sessions right now, so I appreciate you coming to the one and only talk on media at this conference. I am the chief architect in the media division at Akamai. I've been there for 10 years, and I'm based in San Francisco. So I'm going to talk about a subject that even if you're not particularly in the industry, I think it affects us in our personal consumption of media, especially sport, which is low latency streaming, and especially low latency with adaptive segmented media. So for this talk, you should at least have some knowledge of adaptive streaming, such as Apple's HLS or MPEG-. These are formats in which media is delivered as lots of little segments. And traditionally, this media has been well delayed behind broadcast. We're all very tired of the story where you hear the soccer goal being scored on in your neighbor's TV, and then a minute later, you get it on your television, okay? So what I'm talking about today is that type of latency is over. We certainly have the technology and the solutions to move beyond that right now. And I'll get into it. So just some clarification for the media production process. I realize I'm also speaking in English, and most people here are not English, so if there's something I'm saying that is not clear, please ask me to stop and I will repeat it, or I will use simpler words. This is a standard production for media from the camera through to the CDN. What I am referring to when I say the word latency is not the connection latency of the last mile. I am referring to what we call the end-to-end or the glass-to-glass or the hand-waving latency. I wave my hand in front of the camera, and I come over here, and I can see it on my cell phone. When I say latency, it's that delay that I want to reduce. This is an old diagram if you're in streaming industry about latency, but I'm going to throw it away and instead come up with a new one and define some terms for what we mean. So on the bottom, we have latency from 45 seconds down to 200 milliseconds. And up here, we got some categories. So I'm going to define sub-second to obviously be latency less than 1 second. Less than 1 second from it happening to us seeing it on a mobile device. Then I'm defining ultra-low latency as being from 1 second to 4 seconds. Low latency is being from 4 seconds to 10 seconds. And then legacy latency, 10 seconds and up. And bear in mind today that if you go online tonight or this afternoon and watch some streaming video, it's mostly going to be 20 to 30 seconds or higher in latency. And we'll get into the reasons for that and how we can change that. So that's where we want to be in terms of latency. We can look at different applications now and where they sit in the latency space. So if you're doing voice communication, you need to be in the 200 to 300 millisecond range, or else it sounds really bad. So this is the world of Skype. Then we do live auctions, gambling and betting, horse racing. This is where people need to be very close to live. Otherwise, someone is going to profit from the delay that other people have. And then live sports, both traditional like soccer, football, volleyball, rugby, and esports, which is now driving a lot of traffic around the world. And we can overlay over this where our broadcast industry are able to provide for latency. So by broadcast, I mean cable to your house, direct-to-home satellite. This ranges from about 3.5 seconds. Actually, in Europe, with DVB-T2, you have some of the fastest satellite that exists in the world, faster than North America. But in North America, we can go all the way up to 10 seconds for a cable-based feed because the media is being transcoded. As it's being delivered, it's going up to satellite, coming down, going out to head ends for distribution. So we can notice that the broadcast doesn't, in fact, cover all the applications that we want to cover for media distribution. Now we can overlay adaptive segmented media on top of this. So traditionally, when Apple came out with HLS, they used 10-second segments. And because the Apple player likes to get 3 segments of latency in its buffer, we got latencies at least in the 30 to 45 second range. One way to reduce latency is to simply decrease your segment size. So if you go 6 seconds, 2 seconds, or even 1 second segments, you can reduce your latency to in the 4 to 8 second range. And you can do this across the Akamai network today. But what's interesting down here, if we go to the low end of the scale, come on, pressing the wrong button. Down here, below 1 second, the technology you really want to look at is WebRTC, which stands for Web Real-Time Communications. That's your best bet below 1 second. But from 1 second and up, we essentially have this new branch of solution called chunked encoded, chunk transferred CMAF. I'll explain what that means. But that's what I'm going to focus my talk on today, because this allows us to get latencies right down to 1 second, or at least in the 1 to 6 second range. We can also go up to 30 seconds with it if you choose to. But it allows us to address all of these business applications, and it allows us to beat broadcast in terms of latency. So we can get better quality with OTT, and we can get a lower latency at the same time. This diagram is simply showing what I mentioned previously about reducing segment duration. So we have an encoder going into the first mile, CDN, last mile, and into the player buffer. And if you put in 10-second segments, you will get about 50 seconds latency. If we reduce it to 2-second segments, you'll get about 11 seconds. Notice the player is causing most of the latency here. It's not the CDN, and it's not the encoder. But what I want you to learn from today is it's possible to reduce the latency without shortening the segment duration. And in fact, we can decouple the two. Our latency can be entirely separate from the boundary we choose for our segments. And sorry, I gave this talk, it was called Chunky Monkey, so that's why you're going to see a lot of monkeys around, in case you're wondering why does he have these in his talk. So we're also dealing with a file format called CMAF. And you might have heard the word CMAF misused. CMAF is not another format like HLS or DASH. CMAF is simply a file container. It's an ISO-based media file format box, and inside it you put audio, video samples, or in fact text captions if you want. And by itself, it will do nothing to reduce latency. So CMAF is ISO-based media file format. Long word, you might think of it as fragmented MP4. It's been supported across the Apple ecosystem for the last 2.5 years. It's been supported by MPEG-Dash for the last 6 years. So it's a well-established, well-understood file container. And its normal claim to fame, so here we have Apple HLS. It uses file containers called TS, transport stream containers. And it has a manifest, which is an M3U8. So together, these comprise a stream that your device will play. On the MPEG-Dash side, we use a different container, this MP4 container. And the trouble is, a content owner who wants to reach the broadest array of people, he has to make 2 copies of his files. The same audio and video content, but one stored in TS segments and another stored in MP4. So he pays twice to encode it and twice to store it. By switching to CMAF, we merge the two. We have a common set of MP4 files, and now we write 2 manifests against it, M3U8 for HLS and the MPD for Dash. So these are little text files. We don't mind making 2 of them, but these segments are about 1,000 or more times larger than the text files. We only want 1 copy of these. So this is the traditional reason why we use CMAF. But embedded in the CMAF spec is something that's very useful for low latency. And this is called chunked encoding. So here's a normal media segment. It has something called a MOOF, which is an index. And then we might have 6 seconds of video. And right at the start, there's a IDR, or you can think of it as a keyframe. It's a point at which the decoder must start decoding this content. And normally, the encoder will make the last byte here, and once he's taken 6 seconds to do that, then he'll give it to the CDN for distribution. So we immediately have latency equal to the duration of our segment. What we can do instead is make a very short MOOF with a very short piece of video content. It might just be 1 frame of video, which is 40 milliseconds here in Europe. And after making that, we will give it up to the CDN. So we can give it that much faster. The CDN can then give it to the player, and the player can start decoding it. In fact, the player can start decoding this segment before the encoder has even finished making it. So I want to show something that might surprise you. And again, this is getting into how players play back media, which if it's not your world, it might be a little confusing. But let's imagine we have an encoder that's making segments, and it's making segments that are 2 seconds long. So and we're observing it, we're looking at it in the middle of the production of the 5th segment. So it hasn't finished making this. And now our player arrives, and you say, play, I want to watch my football game, start playing now, and play is lowest latency. So if you're an Apple player, if you have an iPhone, it has a very conservative scheme for starting up. It wants to get the last 3 segments that are fully available. So for us, that will be numbers 2, 3, and 4. They're the ones that, the last ones the encoder's finished making. So it will grab those ones, and when it does, it's going to have 7 seconds of latency. This is with 2-second segments. Now, you're a smart engineer. You can say, I can see how we can improve this. Let's not get the last 3. Let's just get the last segment. So if I just get segment number 4, then my latency would be reduced to 3 seconds. But I had to give up something to get there, and what I gave up is the buffer size. So here I have 6 seconds of buffer before I start. Here I only have 2 seconds. So I've traded stability and robustness for reduced latency. And that's always a trade you have to make when we're dealing with OTT and latency. But now let's imagine this encoder was making these chunks I just spoke about separately. So I've imagined that it's making 4 chunks in its 2-second segment. So each chunk is 500 milliseconds. I called them A, B, C, and D. So now when my player wants to start, it has to start with an A chunk because that holds the key frame that it must decode from. But it could pull 5A and 5B because they're ready, they're available. And when it does that, it would have 1 second of latency. Now it can get even lower than that because even though it's got 5A and 5B, it could essentially decode faster than real time. It's got the data. It can seek forward into them. If it does that, it'll have latency less than 500 milliseconds. A second way it can reduce the latency is to wait for the start of the 6th segment. It can make a well-timed request for 6A, and when it does that, it would also have less than 500 milliseconds. So what's interesting is we can have the same 2-second segments coming out from an encoder. We can go anywhere from 7 seconds of latency to 500 milliseconds, all by changing the startup logic inside our player. And many of you, if you work for a company that does streaming, you spend a lot of time buying a fancy encoder, or you spend a lot of money paying your CDN, when in fact you should spend a lot of time worrying about the startup logic in your player. So it's one thing to say we want to, computer went to sleep, wake up. It's one thing when we say we want to make these chunks, but how do we move them out? You know, Akamai does HTTP distribution, and normally you come in from an encoder to the first mile to something called an origin server. And the data sits there, and then the rest of the traffic is your player and your device pulls it from that. So we have push on this side and pull on this side. And what we can use is a very old, 14-year-old HTTP technology called chunked-based transfer. So in a chunked transfer, the server doesn't know the size of the object that it's sending. So it just sends little bursts of data, and the receiver keeps receiving them until it gets a 0-byte chunk, which is a signal from the server that it's done. And this is an old solution, but it fits very neatly with getting our encoded chunks out to the client. So it turns out we can use an HTTP CDN to distribute this chunk encoded content to players, and we can do it at high scale. So I made up a simple analogy here. If you are not in the engineering side, the monkey is thirsty, and we need to get water from the tap down to the monkey. So traditional encoding is to make your segment, fill it up, give it from the encoder to the CDN. The CDN receives the segment, gives it to the player buffer, and once the player buffer is full, it gives it to the decode buffer, and it starts playing. Now, how does this look differently? With chunked encoded, chunk transferred, we can model this as a bucket with a hole in it. So now when I put water in, it flows from my encoder to my CDN to my source buffer much faster. And that's the simple analogy of what I'm speaking about here. So what does this look like? If I go back to that fragmented MP4 structure that we spoke about earlier. So this is a race now. On the top, we have the big segments. You'll notice this player hasn't received it yet. On the left-hand side, it got this little series of these indexes and the media content. And the time difference between these two is roughly 1 segment duration. So that's the speed up we get, or the reduction in latency we get by following this approach. So there's some interesting side effects from this. So one of them is that when I use standard adaptive segmented delivery, I get very spiky performance across my network. So here I'm looking at a Wireshark capture, and I'm playing a stream, and you'll notice it's got segments that are 4 seconds long. So every 4 seconds, I get a big burst of data because the server has the entire segment. It can send it as fast as it can to the client, and the client receives it. In between those periods, there's no activity. And this becomes dangerous because imagine you're another client on the same network that's competing for bandwidth. And you choose to do a bandwidth measurement here in one of these pink gaps where the other player is not playing. It'll look to you like you have all the available bandwidth for yourself. But as you start playing, if you suddenly then make a segment request at the same time as another player, now you're both competing. You will get half. TCP is a fair protocol. You will each get half of what's available, and you might end up rebuffering. So these periods where there's zero throughput are not good for HTTP clients that are competing. And when I mean competing, this is you're watching a show in your bedroom, your kids are watching one somewhere else in your house, and you're both sharing the same internet connection. Both of you have adaptive clients that are competing for scarce bandwidth. Now, if we compare this network profile to a chunked profile, so this is an actual Wireshark trace of me playing the video here, you'll see we don't have the big spikes. We have some variation, but not nearly as many. This was also with 4-second segments. So we get much more consistent throughput. So from a network stability point of view, we like to see consistency. It's much easier for us to manage a 20 terabit system when we have consistent levels than when we have a sawtooth or spiky level. Yeah. Yeah. I'll go back.
So what puzzles me is that the rate, the throughput of the below graph is almost doubled when compared to the top one. And
that's because the bit rate of the lower stream was double the top one. So it's not exactly the same stream.
Okay.
If it was the same stream, then yes, the bit rate would have to be consistent.
The concern was that we need to sustain higher bandwidth, higher throughput all the time when we have chunked delivery, in compared to the previous solution, which requires to support peaks, but they are still lower. But if those are different streams, then that's okay.
Yeah, firstly, they're different streams, but you raise a good point. So let's have a separate thought experiment. Let's say we have a 1 megabit per second stream with 4-second chunks, and you've actually got 10 megabits per second of throughput. Okay, so your client, when he requests that 4-second segment, he's going to receive it 10 times faster than its duration. So he's going to receive it in 1/10 of 4 seconds. 0.4 seconds, say. He's going to get it very quickly. If we're doing a chunked-based transfer, no matter how much throughput he has, he's going to receive the video at the same rate the encoder is making it, which is at 1 megabit per second. So that's, and it raises an important problem later on, which is normal players they time the download of a segment to estimate how much throughput they have so they can switch up and play a higher quality. That's not going to work with the chunked approach. So while it's a benefit for us to get the stability, we always have 1 megabit per second flowing through our system. It causes a problem for bandwidth estimation later on that we need other ways to solve. So I'm going to do a live demo later, and I will show you in Chrome the segments coming in, and we will see the bandwidth level. So remind me to show you. Yes, another question?
I have a question regarding the size of the data, because if we have more keyframes, it means that we have less delta frames. So basically, we have to transfer more data.
So we don't have more keyframes. You only have the one keyframe at the start of the segment. That hasn't changed.
Yeah,
What
but
happens is
previously we had less segments.
yeah, but we have no. So let's not use the word segment casually. In CMAF, there's a chunk, which is a sub-segment. One or more chunks make a fragment, and one or more fragments make a segment. So the segment, say, will be 6 seconds long. It might have 200 chunks in it, each 50 or 40 milliseconds long. So what does go up, and I have a side, actually this next slide, does chunking affect segment size? So the answer is yes, it does, but not because we have more keyframes, because we have more index blocks. It's taking a loaf of bread and saying, I'm going to slice it up into slices and hand you one by one instead of giving you the whole loaf. But I have to write a little index for every slice. So if we look at this, this is for audio. Okay, audio at 32 kilobits or 97 kilobits, I get a 43% increase in my overall bits delivered. Why? Because my overhead for chunking is that, but 14 on top of 16 is significant. But when I go look at my video down here, which is at a megabit, 30 frames per second, it's only 2.7%. Because my overhead is essentially the same, but the video is 500 times larger than the audio, 100 times larger than the audio. So, and even for 60 frames per second at 1500, it's only 3.6%. And if this video was 5 megabits or 6 megabits, like it actually is for 1080p, this number would be well under 1%. So the point with this is we don't, in practice, pay a large penalty for the chunking. Certainly 1 or 2% is acceptable in return for the latency reduction.
Okay, thank you.
So, another question.
Just a very short question, because where do you adapt? Do you adapt at segment, at chunk? Do you adapt at fragments? Just to
Very
know
good
the
question. You still only adapt at your segment boundary.
Okay.
So with CMAF-based segments, every segment must start with a keyframe, and therefore you can only smoothly switch content at a segment. Perfect. So if we have 6-second segments, we can only switch at every integer multiple of 6 seconds after that.
So this is kind of decoupled. So the adaptation on the client side.
So with traditional segment, my switching boundary is the same as my latency, but now we're decoupling them, but I still switch. So it's a reason not to have larger segments, is because I might want to switch quicker.
Okay.
Any more questions? Right. So here's the bandwidth estimation problem that I spoke about earlier. So here's a screenshot. This is a client that has 3 megabits of connectivity to the edge through its Wi-Fi or something. And it's playing 6-second segments. And these segments are going to come as fast as the encoder can make them. So we see in practice that they come in just less than 6 seconds. Here's a client with more than 10 times the throughput, 50 megabits per second. And notice the segments don't really come any faster. And that's because they can't. The encoder is making them. It's making 6 seconds of data every 6 seconds, and the server cannot give it any quicker to the client. So having lots of throughput, more throughput than the encoded bitrate of the content, doesn't get it to you any faster. Now this is a problem because, as I mentioned, normally a player is timing the download of the segments. Because with traditional adaptive streaming, the server has all the data, so it can burst it to the client. And the ratio of the time it takes to receive it to its playback time is an estimate of your throughput. And if you apply that same logic to chunked encoder transport, you'll get the answer that the throughput is always equal to the bandwidth of the video that you're playing. And therefore, your player will never switch up. So we need some other schemes to estimate bandwidth. So here's 3 of them. The first one is what Amazon are doing with Twitch. Twitch is a big live game streaming platform. They opened up a machine learning challenge for ICME, which is a academic technical research conference and paper publishing. So here's a chart of these bursts that are coming from the server to the client. And they want to use machine learning to infer from this burst pattern what the actual throughput is. So that's one way to do it. A second way is what an open source player project that I run called dash.js. This has what I can say is a simplified averaging. Because when we're estimating the throughput, we don't want to make the mistake of overestimating it. We're okay underestimating it. So if we're okay underestimating, we can be quite conservative in our estimation. So what we do is we take the chunk sizes, we discard the outliers, the ones that appear wild, and then we keep a sliding window and we average over that. So this is all open source code. It's available on this GitHub project. And that's one way. A third way is what I call it simple side load. That should be side load and not slide load. And in this case, you simply download a test object while you're playing your stream. And then you add, that object's fully available. So it will come quick. The more bandwidth you have, the faster it will come. And you can use that to estimate how much bandwidth you have. But it's important that you do this very carefully because we're dealing with very short player buffers now. And we don't want to cause our player to rebuffer because we're doing a bandwidth test on the side. So you have to do a very small bandwidth test of 10 bytes or 50 bytes or 100 bytes. If that works, you double the payload size. And you keep doubling it as long as it doesn't disturb your latency until you get a more accurate answer. And then you can switch up or switch down. I say switch up. Switching down you can do by just looking at your buffer length. If your buffer length starts dropping, you're in trouble. You need to switch down. So 3 different ways to solve the bandwidth problem. So it's an acknowledged issue, but there are solutions to it. Another one is catch-up. So the traditional thinking is there's only one chance for a player to define its latency for a live stream, and that is when it starts up. And this is different to a video-on-demand player. A video-on-demand player can start playing your video very quickly in 1 second, and then while you're watching it, like a Netflix movie, something like that, it builds a 3-minute buffer in the background. Because it can. All the segments are available. It just downloads more of them. Downloads them faster than it's playing them back. You can't do that with a live stream because once you start playback, you're decoding the content at the same rate that the encoder is making it. So you stay the same distance behind live. Now that statement's true unless you speed up or slow down your playback rate. So now you can start to adjust. Once you start playing, if you want to get closer to the live point, you start playing faster than real time. And if you want to pull yourself back from the live point, you start staying slower than real time. So here's a chart. We've got the live stream latency on the y-axis, and this is wall clock time on the bottom. And this is a player that was told to keep a target latency of 3 seconds. And it started out at 6 seconds. But notice it very quickly adjusted its playback rate to pull itself down to 3, and then it adjusted the playback rate to 1 to stay at that point. And here it had an error. I caused it to rebuffer. I caused a segment to come slowly. When it did, it figured that out and again quickly accelerated its playback rate to get back to constant. So this notion of changing your playback rate to keep a target latency is a new behavior that players need to learn. But it's not hard for them to do it. I'll show you one working in operation. And it has a very pleasant side effect as well, which is synchronization. So, synchronization. So if we take this ability for a player to adjust its position to live, and we give players in a room a common target, and we give them a wall clock time reference that they can trust, then the end result is synchronization, meaning players play the same video at the same time. And this is an often recurring problem in OTT, which is I can watch the same game, same football game on 3 different services, and I see it at different amounts of latency. So here's a screenshot. I have a player that I can show you. It's playing on a big computer and 2 different laptops. And you notice the timestamps here. They're all within 60 milliseconds of each other, which is 2 frames. I was dealing with 30 frame per second content. And this is not a fancy synchronization scheme. I'm simply telling the players to keep a fixed latency and giving them a external wall clock time reference. And there's no web sockets or anything talking between these players. They're not communicating with each other. They just have a time source, they have a media, they calculate latency, and they try to keep a fixed latency. And we can get sync out of it. Another issue is video start time. So if I tell you, ooh, I've got 6-second segments, and if you're an engineer and you say, oh, I guess your average start time is going to be 3 seconds. Won't it be 3 seconds? It turns out it's much faster than that, so let's look at why. So the time it takes to start video is a function of three things. It's a function of its segment duration, how much buffer you actually want to have when you start, and the throughput that you have, meaning how well your client is connected to the server. There's also an even probability that you will start anywhere in this segment. So this is you open up your phone, you want to watch something, you hit play. Underneath that, there are these segments flowing like a stream. You don't know where the segment boundary is. And remember, we must start decoding from a segment boundary. So here's a 6-second segment. And I can randomly drop into the 6-second segment at any point in time. And I want to figure out what my average latency is. So say I drop in here, roughly at the 3-second mark. In this model, I want 2 seconds of buffer at the start. Well, I've got 2 seconds. In fact, I've got 3 seconds. So I could start playback immediately. This data is all available for me to request. I request it, and I start playback. But if I happen to want to play this segment right here, it's less than 2 seconds. I would have to physically wait more than a second here for that data to become available before I could get it and start playback. So in general, we can say that any clients from 0 to 2 are going to have to wait to start, and any clients in the green area could start playback immediately, or at least start downloading the content. So I'm ignoring the time it takes to download it. It's just a thought experiment. So 33% must wait 1 second. The other 67% essentially wait 0 seconds. The average of that is 330 milliseconds. So even though we have 6-second segments, and I need 2 seconds to start, on average, across all my clients, they'll take about 330 milliseconds before they can download content and start playing. And we can generalize this. So here's a table. I got a segment duration from 1 second to 6 seconds. And then I got a starting buffer that I might want to have. Remember, starting buffer is your insurance. It's your stability of the system. The more buffer I have, the more stable my stream is, and it can survive variation in segment delivery. And these numbers, so when I say like a client, a maximum start time, if a client wants 2 seconds of buffer, there will be some clients that must wait for full 2 seconds, but there will be very few of them. So as opposed to traditional segmented media delivery where I can say all players will take a fixed amount of time to start, as we go in a chunk-based transfer, it's a distribution curve. Some players will take 2 seconds, but most will take a lot less. In fact, if I set a threshold and said, I want the combination of segment duration and starting buffer that gave me less than 1 second startup, then I have a lot of options. So this is theoretical. That's what the maths says on the back of an envelope. This is empirical. I actually took a player and I measured. I did a bunch of starts and I measured how long did it take to start. And this is a player that had 6-second segments with a 2-second starting buffer, which is the case I gave you before. And in this case, my average start time was 850 milliseconds. Now for 6 seconds and 2, it says it should be 330, but that's not including the segment download time. So this just tells me that for my combination of ISP and CDN and computer that I was using when I did this test, I need to add on another 500 milliseconds to this number to account for the segment download time to get my real world download time. But it's still a lot lower. It just means we can start these streams quickly and then play them back with continuing low latency. So something about timing models. And if you're not into this, so there's 2 main adaptive streaming formats, HLS, which is very popular in the US, and MPEG-Dash. And I'm also chairman of the MPEG-Dash industry forum, so I'm a big fan of MPEG-Dash, but I will also talk about HLS. So the HLS timing model is deceptively simple. You get a master playlist, you download it, it gives you a list of child playlists, you download the child playlist, it got a list of segments. You take the last segment, that's your lowest latency. But nothing in the spec tells you when you should download that media segment. It's purely random. So it's like a monkey essentially stabbing in the dark. We don't know what our media looks like. It's a black box to us. Once you download it, you can reveal that back, and then you can see, oh, okay, remember these segments that are flowing through? I have to start at a keyframe now. So just by randomly going there, I've incurred this much latency by when I chose to request that media playlist. So the player, represented by the monkey, has two choices. It can try to decode faster in real time. Now, you can't always do this on all devices. Certainly at 4K, some devices are not powerful enough to decode that fast. Or the player has to make repeated requests for the content, looking for the next segment to start. So it's polling the server, essentially. And it'll look for a change in the media sequence, which is an attribute inside the playlist, or the E tag, or the date header, or some other attribute of that media playlist. So that's with HLS. A lot of people, again, don't care when their player makes a request. They just download the media segment and they live with the consequences. And if you have 20 seconds of latency, it really doesn't matter too much. But if we're striving for latency in the 2 to 3 second realm, then it starts to matter. So Dash is a little different. It's a deterministic timing model. In this case, the client has a precise idea of when the encoder is making the segments. So it's like an opaque box. It can see inside it. And in theory, it should be able to come down and it should be able to nail the segment right at the start. That's when we want it. We want to grab it as soon as it's available because we get the lowest latency. And that's the theory. The trouble is it requires accurate timing. And in practice, you can never trust the client clock. So here's a screenshot of my mobile phone, which you think it's synced with GPS. Surely it's accurate. There's an app called Clock Sync you can put on. I can't fake this stuff. I have a half a second of delay, of inaccurate time on my player. So if I'm trying to get 1.5 seconds of latency, that's a 33% error there on a mobile device. And laptops are worse. New laptops, old desktop PCs are downright terrible for time. They can be 10 seconds, 20 seconds, 30 seconds off. So at Akamai, we've open sourced a timestamp, time.akamai.com. You can append the and milliseconds attribute, and it'll give you a timestamp that's accurate down to milliseconds. Well, at least has a resolution down to milliseconds. It's not accurate because there's a time taken to construct this response plus return it to your client. But players can use this. Instead of trusting the local clock in your device, you can go and hit an external time source from a CDN that is more accurate because this is NTP synced. And this allows players to then, the player example where I showed the synchronization, their common time reference is that time source there. So I've spoken about Dash. There is something called low latency HLS. So this is what Twitter and their Periscope product use, or what Amazon and their Twitch product use. And it's essentially how HLS describes these segments that are not fully finished. So normally with HLS, you can only describe a segment that is complete. But they introduce a new tag here called prefetch, and this describes segments that are in the process of being released. So a standard player will see this. It won't know what this tag is, so it will ignore it. But a player that's built for low latency will know what to do with this, which is to fetch it early and to begin playback. So there is an initiative. Sadly, there is no standard for this. So JW Player and a guy called John Bartos are trying to standardize LHLS so that encoders make it a certain way and players play it back in a certain way. But that standard does not exist yet today. So some of the benefits of chunked encoding. One of them is legacy player support. So I've shown you examples where I'm trying to play low latency, but what if I don't care about that? What if I'm a player that's happy being 18 seconds behind live? That's fine. You can play a low latency stream at any delay behind live that you like. You do not have to play it at low latency. So here I took the same stream. This is my test harness here, playing like at a base like 1 second past the minute boundary here. Here's two other players. This is Bitmoving's player. This is Shaka player from Google. You'll notice that's 24 seconds behind. That is like 12. And this is Apple's QuickTime player here, which is also. But the important part is all of these players played the stream. So one of them was set up to play super low latency. The rest weren't, but they were still robust. It still worked for them. So it's backwards compatible with existing players that know nothing about chunk-based transfer. That's because chunked encoding is part of the H.264 standard, so all their decoders are capable of decoding it. The other one is CDN cacheability. So these, remember, the player is not requesting chunks from the CDN, it requests a segment. And the CDN receives the segment in the form of little chunks. It sends them up to the client as fast as it can, but the unit that it caches them with is the full segment. So this means players arriving more than one segment duration behind live, they get the full segment as they've always done. This means it's cacheable, and this means we can hit high scale. And here you see an example. So here I've got a player playing these segments. So there's segment 575. And for a player that was playing close to live, it came in just under 6 seconds. On the same device, same connection, a player that is 18 seconds back, requesting the same segment from the same CDN over the same connection, it comes in 1 second. It comes in 1 second because it was cached by this guy pulling it to the edge. So the CDN caches it, and now he can burst it because he's got all the data, and this client's got more throughput than the bit stream is encoded at, so we get it quicker. So this just shows that the cacheability is working. And CDNs are compatible. So this, Akamai is fully compliant with this chunk-based transfer today, which is one of the things that separates us from some other CDNs that are out there. These HTTP transfers have to be chained together. If any one component on the step doesn't move the chunk along as fast as it can, then our latency is going to break. But the point is, if you want to hit millions of viewers on a low latency stream and leverage existing cache infrastructure, then chunked CMAF is a good way to go. It doesn't require a new distribution system. It's not UDP based or RTP or RTSP or WebRTC. Couple of other benefits, I'll just list them. I've mentioned decoupling latency from segment duration. We don't have to make increasingly shorter segments now to get our low latency. The segment duration does affect the switch frequency, how quickly we can switch up or down or react to changes. It does support common encryption, which is the ability to mix play-ready widevine and fair play together in the same media segment, something that TS segments and older HLS TS doesn't do. So we can support protected and encrypted media. It retains UHD features, ultra-high definition features like 4K, wide color gamut, and increased bit depth. It also allows for codec diversity. So I mentioned CMAF is just a box. You can put inside it AVC or H.264 content as well as HEVC and now upcoming AV1 content as well. I realize I'm running out of time, so it's standards-based, yay, and it supports server-side ad injection, which is also good. We haven't changed the playlist structure. It's being standardized in a lot of places, including DVB here in Europe. So DVB-I is coming out. It's the internet-based version of DVB as they transition from broadcast to broadband. It's going to use this approach to achieve low latency. There's vendors who support this today for encoders, for CDN, and for players. And there's a whole bunch of open source code. So here's an open source encoder. Akamai contributed code to FFmpeg, so you can run this on your own laptop. Open source is all about real people doing work for free, essentially. So I like to give them credit. So this Karthik is the main guy here who did the work on this. An open source player, Dash.js. It's fully available. This is Jesus. He's in Madrid. He's team lead. These are all the people who work on the project there. And then open source server. So this is a collaboration with Colleen, who has red hair, from Facebook. And we worked on this thing called Streamline, which is a server that allows you to get segments and distribute them. So if you want to play with this, you can do it for free and from any Linux machine. So I won't do pre-canned demos. I was going to try to do a real demo. So here I have Chromium, Chrome browser. There's nothing fancy. And I'm going to load a stream that hopefully will play. So this is a stream that's being encoded in Boston with 6-second segments. And I've told it to get a latency target of 3 seconds. You'll notice that feature of changing its playback rate. It quickly pulled itself to the 3-second mark. Here we are charting out latency and against wall clock time. So once it gets to its target latency of 3 seconds, it should just sit there. And it'll try to keep that unless there's some perturbation to the system. But even though I'm playing over hotel Wi-Fi, this is a stream. The number in the top left is the time code burnt in at the front side of the encoder. This wall clock time is an overlay I've put in the page, so the difference between them is this number here, which is the 3 milliseconds of latency. So this is faster than you will get any content from satellite or through any distribution means other than WebRTC right now. But the advantage of this is flowing through Akamai's Media Services Live. It's coming all the way from Boston here to us in Krakow. And it's not, this is maybe 600 lines of JavaScript. This is a very simple test harness. If you want to see the source code, I'll show it to you. If you want to see a professional player that has all the features in that you might expect from media, here's the same stream being played by dash.js. And this has audio now. My last one doesn't. Can we just turn down the... So, same thing. Sorry. I can't turn the audio down from here. Can you? I can't. I have muted it. Look. It doesn't... Oh. Ah. I can mute the stream. Yeah. Yeah, the player actually has a control, I forget. So I set this has configurable latency. I said I want you to keep a latency of 2.8 seconds. So you'll notice there's the 3 second, it's keeping its 2.8 seconds. We've got audio, video, we've got captions, we've got subtitles, we've got all the other things you might want in a media player. And again, that's open source, you can check it out. I'll go through here. And I think I need to conclude because we had 2:45. So in summary then, you should understand now what chunked encoding and chunked transfer are two different things. Understand low latency. There's many aspects to it and complexities on the player side, but it's a solvable problem. And that we can get latencies below 1 segment duration. And I think practically operating at about 3 seconds of latency is sustainable, of which 2 seconds is the player buffer. The rest is CDN and encoder logic. And with that, I know it's coffee break, so I can take general questions, or you can just come up here, and I'm happy to answer them. Okay, well, you've all been very kind to sit through a media engineering talk, so thank you.